right, welcome back. In this lecture, we're going to talk about curried functions. And before we go into the code on curried functions, I want to talk briefly about what these function signatures and how they tie into currying and a little bit more detail on what functions are really all about. And to do that, I'm just going to do some drawing on a whiteboard. Well, in this case, it's a blackboard. Let's take a look at that. So we talked a little bit about function signatures and what function signatures are all about. I want to go over that just briefly again before we talk about currying. A function signature that looks like this: tick A, arrow, tick B, says that these are types. It could be int to int, or it could be character to character. These generic types are just saying that this function can take any of a type A and returns any of a type B. They could be the same type or they could be different types. If you see something like tick A to tick A, that means that the type is the same. It's the same type. The little tick marks mean they're generics. And in C#, that would look something like this. We might have a method that, and I'll go ahead and use the lowercase a, but without the tick mark. We could have a method that returns a type A, which we probably wouldn't normally use, and we'll call it some function, fun, and it's got a generic type A. Well, in this case, for this first one, this should be a B as the return type. Let me erase that. And we'll make this a generic type B. And this has to take, we have to specify both A and B in the generic. So here's the A, comma, B. And this might be our function signature, and then it might be A and some value V, and B, type B of some value Q. And that would be a C# style generic. Only we would probably use capital letters. It would be something like T, fun, T, comma, R. And then some function in T and R, TA, TR. In that. These are equivalent in generics. When you see something like int to int, that means it's specified. It's not a generic. It takes an integer, it returns an integer. And if it takes more than one parameter, you might see int, int, int. This would be a first parameter, a second parameter, and a third parameter. So that's function signatures. With currying, we'll just erase that. With currying, what we're really saying is that we've got some function that takes a type in, we'll call it an int, and it may take another type in, that's an int, and it returns an int. But in reality, what we're saying is that this is a function, just like the previous description of it, and that really this function takes a single int and returns another function that goes from int to int. And these could be generics. It could be tick A, and then it could be tick B to tick C. And that would be the generic equivalent of a function, a curried function, one that takes a single parameter and returns a function that takes a single parameter and returns a value. That's what currying is all about. It's about breaking a function down that has multiple parameters. So if we have some function on x, y, z, the way this would be represented is x, and these are actually variables, and these should be types, so we'll call it tick x and tick y and tick z as the type, and this is a curried function, actually, and then it returns some value. We'll call it tick v, the value it returns. So this is a function in 3 parameters, and it's actually a function that takes 1 parameter, this, that returns a function that takes 2 parameters and returns that, which in actuality is a function that takes 1 parameter and returns this function right here. So that's how it gets down to this single parameter function. The z is the function returned. It brings in the y, then it brings in the x. And this is, of course, the first parameter, the second parameter, and then the third parameter. So let's go take a look at Visual Studio now and see what this looks like in terms of code. Okay, here we are in Visual Studio. And what we're going to do first is take a look at Solution Explorer here. So we're in Module 2. We've already got our test console application and our scripts folder. So I'm just going to go in here and add another script file. We'll just do an add below, new item. Make sure we're in Visual F# items and select script file. And we will call this we'll call it currying and partial application. So we've got a nice new file here, and the first thing I'm going to do is type in open system because we'll need that. We'll go ahead and send that down to the F# interactive like that. So that's in. Now, the first thing I want to talk about in regard to using currying is this idea of lambda functions. A lambda function, you might be familiar with that from C#. C# uses lambda, or allows lambda functions. A lambda function is nothing but an unnamed function. It's usually something you write in line with where it's being sent. There's no need to give it a name. You're just creating a function and passing it into another function. That's the idea behind it. And here I've got a demonstration of a lambda function. This is called uppercase all. It takes a list of strings as a list. A string list says that this is a list of strings, and this is the name of this value, the list that comes in. And we're taking that list, we're using what's called the forward pipe operator, which is the equivalent of putting this list all the way down here at the end. This just makes it more clear. It says the list is being piped into list map, which is receiving a lambda function. And what that lambda function does is, well, list.map calls this lambda function that gets passed into it for every item in this string list, and takes its return value and puts it in a new list, and that's what is returned by this. So let's put this into the interactive, and we'll take a look at its signature first. So here is its signature. Let's copy this out and put this here in a comment. So it takes a list of strings. It's called list, and it takes a list of strings and it returns a list of strings. So how does it work? Well, list.map, we'll talk about it in more detail as we go through. We'll use list.map in many different functions that we create. It's a very powerful tool. It just takes this lambda function, and this is an unnamed function, and passes it into list.map, and then list.map uses it for every one of these list items. Now, this forward operator we're going to talk about operators towards the end of this lecture. This forward operator just switches this around, and it puts this list at the end as the second parameter on map. So let's see how this works. We run this in, and it took every string in that list. Here's a list of strings, and it turned them into uppercase by calling this upcase to upper function on each one of the strings, returning it to list.map, and list.map added it to a new list and returned that new list as the output of this function. lambdas are extremely useful in many ways. And so here's a little bit more on lambdas. This is another way you can use a lambda, is to define a function. I'm just saying let my lambda, which is a value, as we've said before, and I'm assigning it to the value of this, a function in x, where x times x is its output. And if we run that in, you'll see what we get is that my lambda is a function that takes an int and returns an int. This is equivalent to the shorthand version of writing let my lambda, we'll call it 2, equal x times x, the square of x. Those are, those are my lambda 2. We got to give it the variable. There we go. My lambda 2 equals x times x is equivalent to this. This will return exactly the same signature. It's my lambda 2 takes an int and returns an int. It's the same thing. And of course we can call my lambda and we get 4. We can call my lambda 2 and oh, I never ran it in, did I? There it is. My lambda 2. Oh. Interesting. Error. The value of the constructor my lambda 2 is not defined. I put an n in there instead of an m. Let's redo that. Okay, a little typographical error. They happen. It's important to read those error messages and check them and see what you did wrong. So that's what a lambda is. A lambda is just an unnamed function, and the format of it is we say fun, then a list of variables that are going to be used within that function, and it can take more than one. Not variables, but values, arguments. And then the function body goes after the arrow. And we can enclose this in parentheses, and sometimes it's important to do that, especially if we're directly passing it as an argument. The parentheses here are not like the parentheses in C# that surround a parameter list. These parentheses are the typical mathematical parentheses that just say group this all together as a single item. And so it says that this is a single argument to list.map by having the parentheses around it. If I were to take those off, it would get confused and it would think that fun was an argument. And it's expected incomplete, unexpected keyword fun and binding, expected incomplete structured construct at or before this point, or the token incomplete, expected incomplete structured construct. I'm not sure why it says that, but by putting these parentheses around it, we group it all together, say it's a single argument, and that's the function argument that's being passed into list.map. We can rewrite this as well. We can take this off of here and just put list out here, and this will work just as well. And we'll go ahead and test it. Yep, it works. Yep, it still works. Okay. But I'm going to put it back where it was. List. Pipe through list.map. We'll take this list off, and everything's good. All right. So that's what lambdas are, and lambdas become very important in many of the things that we do in the future here. So now, currying. Currying is named after Haskell Curry. Curry or Curie. Currying is named after Haskell Curry. Curry. I'm not sure how that's pronounced exactly. And when we have a function, what Haskell Curry was a mathematician. The language Haskell is also named after him. He was a mathematician that came up with this idea that all functions really only take one argument. They can always be broken down into a chain of single argument functions. And that's really important in certain types of analysis in mathematics, and that's what he was driving at. But it's also important, it turns out, in analysis of computer programs, because if we can work with single parameter functions, they become much more flexible. And in the end, a function that requires many parameters can be broken down to a chain of single parameter functions, which is very useful. And so this is a curried function. Let a equal ab. Let add ab equal a plus b is a function. Excuse me, it's not a curried function. Well, it is in F sharp, but we'll get to that in a second. How we would curry this manually, and this is called add curried, it only takes one argument, and it returns a function, a lambda, with an argument b that does our a plus b. And we can see, we'll put this one in, that's our function signature, we'll put this one in, and that's our function signature. They're identical. This function signature is equivalent to this function. They're not equivalent, they're identical. They're the exact same function signature, even though I wrote this one differently. This is important because F sharp gives us this for free. And what we mean by for free is I didn't have to type anything. I got the same thing as doing this with just typing that simple syntax. Putting the function together like this, F sharp automatically curries all functions. All functions. They're automatically curried, and that way we can do a thing called partial application, which we're coming to very shortly. So here's the next one. We can have I'll go ahead and put this comment in here. So we get, in F sharp, we get we get curried functions for free. So the compiler does it automatically for us. If we had to manually do this currying, turning them into a chain of functions, and we had a bunch of arguments like A, B, C, D, so this add four numbers adds these four numbers together. To do that manually, we would have to write a function like this. We would have to have add four numbers A equals a function that takes B, which returns a function that takes C, which returns a function that takes D and adds A, B, C, and D all together at the end. If we take this and put it in, that's what we get. If we take this and put it in, we get exactly the same signature in both cases. So what's happening is this function here that we wrote is really this function here. The compiler builds this curried function for us, whereas we only wrote this. So sometimes this is referred to as syntactic sugar, and what's meant by that term is simply that we've got a shorthand or some simplified syntax that the compiler can turn into what the full-fledged program would really be if we wrote it all out by hand. So you can see this is a big time saver in creating curried functions. Now there's a difference, and that is, oh yes, and now partial application. So with partial application we can do the same thing. Because of curried functions we can do partial application, which means we can create a new function, and I'll call it add four numbers curried 3, and we'll say we'll have that be add four numbers curried with a 3 after it. So we're baking in a single 3, and here we'll do a 3 plus 4. We're gonna bake in. We're gonna take this function here, and we're going to partially apply it again with a 4. We could do this all at once as well. We could partially apply the two, but I did them separately here. I'll demonstrate that in a second. If we put these two functions in, they don't look the same. This has 4 instead of 5. This 1, 2, 3, 4, and a return value. This has 1, 2, 3, 4, and the second one down has 1, 2, 3. So we're reducing, each time we do this, we're reducing the number of arguments that we need. So we'll do add test equals add 4. We'll go back to the base one here. Add 4 numbers curried, and we'll go 3, 4, 2, 3, 4, but we won't do the last one, and we'll see what we get from this. So this just returns that function that takes an int and returns an int. And if we say add test 5 here, it'll run that function and we'll get 14. So 4 and 3 is 7, 8, 9, plus 5 is 14. So it's doing it. It's running all of those underneath and completing the partial application. So partial application can also work with a thing called operators, and I'll show you that briefly here, and we'll talk a little bit about operators and operator overloading. So I can create a function based on an existing operator. So less than is an existing operator. Operators in F# are functions. In this case, this is a binary operator. It takes one on the left and one on the right. But by putting it in parentheses, I can treat it as a function. And then I can partially apply it with the one on the left, which is the first parameter. The second parameter would be the one on the right. So I'm saying that x is less than this. If you imagine this x being over here to the left side of the less than, whatever x is, I want it to be less than whatever I'm passing into it. So then I can use that to create a partially applied function. So if I say 2 less than, I can say x less than 2, and this gives me a new function. Let's take a look at this first. So this is kind of strange. It says we take in a value and we return a function from value tick a to bool. So it's generic. There's a generic. X can be any value that can work with Boolean. Very likely that's going to be integers or something that has the idea of less than, but it could be strings as well, and we'll demonstrate that. This is called a type constraint. We're going to get into type constraints in the next section, but basically this is just saying that this type tick a must be a comparison type. The system must be able to compare it for that to be able to work. So if we go in here and we do something like create a list, and remember I showed you earlier about lists. So now I've got a list that's got a bunch of numbers in it. And what I want to get back is I want to get back a list of true and false. It's going to be true if the number is less than 2. If 2 is less than the number in the list, it's going to be true. Otherwise, it's going to be false. Let's see what happens here when we do this. And then we do this here. I did not run that one in. Apparently I didn't. There it is. Okay, so now we get a new list. It's a bool list in this case. So this function now has used this list.map to pass in this function that we created here that has this baked in number 2 that's based on this partially applied function that we created here. And what it does is it cranks out this list: true, 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 false, true, true, false. So what do we have? 1, 2, 3, 4. 1, 2, 3, 4. 2 is not less than 2. 2 is not less than 2. 2 is less than 6, 9, and 2 is not less than 0. So it gave me the correct answers for each one of those. So now I'm going to talk just a little bit about operators and operator overloading. We will do this quite extensively. We will be overloading operators and making our own operators. So F# operators, they act like functions, and we can create our own operators. And I've created a custom operator here. It's not really a very interesting one because it's just this weird Boolean operation I've decided on here. It's not X or not Y is what this means. So when we run this in, what we end up with is a function that that takes 2 bools, X and Y, and returns a bool. That's all this operator is a function. And but because it's an operator, and because of this syntax where we put it in these parentheses in the let statement, that's what tells it we're defining an operator. And there's certain characters we can use for operators, and we can string these characters together. The exception is tilde. Tilde is a slightly reserved. It's used for creating unary operator overloads, and only certain operators can be unary operators. We'll maybe touch upon that in more detail later if we have a need for it. We'll see. But so we've defined this operator here. We've got that in, so let's see how it works. Let's run these in, and we can see that false, running this on it, 2 falses produces a true. Well, that's correct, because if it's either a false, if X is false, then not false is true, and true or whatever this is will always be true. And we can see we've got those cases. So it's true, 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 false for the last case. If both are true, then this will return a false. And this operator does that operation right there when it gets run. And so we can also use it as a function if we want to, and that's got some useful things we can do, such as being able to pass and add in like it were a function into another function. We can add a plus in or one of our own operators like this. So if we run this check in, it's just a bool to a bool, but it's got true loaded into it. So if we do check true, we get a false, and if we get check false, we get a true. And that just baked the true into one side of this, so that only with a true are we going to get a false. Any other condition, we're going to get a true out of it. So that's about operator overloading. All right, so we've gone over currying and a little bit about lambda functions and partial application, and a little bit about creating our own operators. We're going to be using all of these, especially when we get to working with types, designing with types. We'll be using operators, creating our own operators. We'll be doing definitely partial application and other operations on functions. So this is an important part of what we're working on. So yeah, I'll see you in the next video.